So an interesting question here, lots of wordiness in the question. So before I even read the question, I'm going to recognize that they've given us a table of potentials, all of which are of course reduction potentials because electrons on the left, on the left, on the left. So let's flip that round so we get explicitly the list of oxidation potentials. Now let's read the question. Blue oxovanadium 4 cations, VO 2+, can be oxidized to yellow oxovanadium V ions, VO2+. So that's the oxidation we're interested in. VO2+, going to VO2+. Got to be careful how you say these things so you distinguish VO2+ from VO2+. It's VO2+, VO2+. Okay, now if this is going to be an oxidation, there must be a reduction. So here we are by bromate 5 ions, BrO3-. Do we know about reduction of BrO3-? Indeed we do. It's right there. Okay, so use these standard electropotentials to identify the made bromine containing product formed when excess bromate 5 ions added to a solution containing VO2+ ions. So this is our oxidation, that is our reduction. Each oxidation produces 1 electron, each reduction needs 6 electrons. So let's go ahead and multiply that by 6. So here is the whole oxidation process. There's the reduction process. Add those together, cancel out as appropriate, and we get that this is the equation. Okay, there's the VO2+ plus the bromate turning into VO2+, and the main bromine containing product, you would say, is bromide right there. Just in case, even though they didn't ask for it, to demonstrate that this can happen, that this oxidation by the bromate can happen, we got plus 1.44 is for the reduction potential, a nice high reduction potential, and -1, still a relatively high oxidation potential, but plus 1.44 better than 1, so plus 0.44 volts overall. So you go ahead and you say, right, the bromide is therefore going to be the main bromine containing product. But, and it's a large but, let's see what we've got there, because not only do we know about the bromide here, but we also have a little equation for bromide being oxidized. Now that's only significant when you realize that we have excess bromate ions in there. So we got enough bromate ions to do all of this oxidation, but then we have some left over, and we have bromide floating around the place. So therefore there is a second reaction that can take place. Still got that excess bromate there that can be reduced, but now we got bromide that can be oxidized. Put those two together and the overall cell potential is positive. Plus 1.44, that really high reduction potential for bromate is high enough to be able to oxidize the bromide, even though bromide really doesn't want to be oxidized too much. Put them together and plus 0.35 volts is the overall reaction, or the overall potential for that second reaction. In other words, bromine is going to be the final main bromine containing product, because while you make bromide, because you've got excess bromate floating around, you can then oxidize the bromide to bromine. Fun one, I thought. So one way of assessing whether a reaction is feasible is to use standard electropotentials. It is suggested that hydrogen peroxide, there's hydrogen peroxide, can be used to oxidize Cr3+ ions. So therefore, the Cr3+ is the oxidation. There's Cr3+ there, plus 1.33 to reduce dichromate to make Cr3+, so minus 1.33 to oxidize Cr3+ to make dichromate. And obviously if Cr3+ is being oxidized, that means the peroxide is being reduced. So we got a little potentials there, add them together, we get plus 0.44 volts for the whole thing. That's a spontaneous reaction. So therefore, yes, the reaction is spontaneous, which means, using the silly little wording, it is indeed feasible. So now another fun question that takes the fun we had 2 questions ago and makes it even more fun. So anyway, potassium dichromate 6 is used as a reagent in acid solution in a wide range of redox solutions. So here is our dichromate 6. Okay, beautiful little species there, dichromate 6 plus H plus, so therefore that's in the acidic conditions. Okay, now these ions can be reduced, so that's what we want, the reduction there, using excess metallic zinc in acidic conditions. Well, we know about zinc, metallic zinc here, but here it's the product of a reduction. Well, that's fine because this is our reduction, so we now need the zinc to be involved in an oxidation, and so we just do our usual bit there, take the reduction, flip it around, change the sign, so plus 0.76 volts. So the first reaction that's going to happen when you take dichromate and metallic zinc is quite simple. The dichromate is reduced, the zinc is oxidized, plus 1.33, plus 0.76. So a very, very spontaneous reaction there, dichromate plus the zinc. Okay, now you'd say that at this point, well, that's it, except of course that it's not just metallic zinc, it is excess metallic zinc. So in other words, we've got a whole lot of this zinc still there that has plus 0.76 volts around to play with. Okay, now let's have a look at what we've got in terms of the chromium. We made some chromium 3 plus. Okay, now that chromium 3 plus can further be reduced by this excess zinc, either to chromium solid or to chromium 2 plus. Now going to chromium solid is minus 0.78, which is more negative than plus 0.76 is positive, but this one right here is minus 0.42. So this is smaller negative than this is positive, so we can have a second reaction that's going to take place in which the Cr3 plus picks up an electron from the excess zinc to make Cr2 plus. Put all those together and the voltage for that is plus 0.34 volts. So therefore, when either Alfred or Fatima takes potassium dichromate 6 with excess metallic zinc, first reaction is they'll make some Cr3 plus, but then that gets further reduced to Cr2 plus. So both of them would make Cr2 plus. However, we're told that they actually get different products in each case. Alfred performs the experiment under an atmosphere of pure nitrogen. Fatima does it in a standard test tube. Electrochemically, both of them are going to get to Cr3 plus. So what happens that makes Alfred's and Fatima's different? So the big thing with Fatima's experiment is she did it in a standard test tube, which means that oxygen is present. And here's oxygen, which can be reduced to hydroxide under the appropriate conditions with plus 0.4 volts. So we got a potential reduction half equation, and then we've got Cr2 plus. Well, of course, we made Cr2 plus via a reduction, but the fact you make Cr2 plus via a reduction means that you can also have Cr2 plus being oxidized. And indeed, Cr2 plus being oxidized to Cr3 plus is plus 0.42 volts. So because Fatima had oxygen present, once she made the Cr2 plus, now we can go ahead with a third reaction, Cr2 plus being oxidized to chromium, because the oxygen is itself being reduced, and the cell potential for that is plus 0.82 volts. So Alfred, his experiment finished at Cr2 plus because it could go no further. Fatima, however, had oxygen present, which allowed oxidation of that Cr2 plus to Cr3 plus. Wasn't that a blast for a question?